Welcome back, and thank you for joining us for part two of our high-level exploration into decision-making in the era of artificial intelligence. This is the fourth section of our AI Made Easy presentation series. I'm delighted that you've returned after our journey through the foundations of uncertainty and probabilistic reasoning in part one. As we embark on part two of this presentation, I'd like to take a moment to once again set the stage for our journey together. The primary objective of this series is to demystify the complex world of artificial intelligence, offering you a comprehensive overview of its key concepts from a strategic, high-level perspective. In crafting this presentation, I've made a deliberate choice to initially set aside the intricate mathematical formulas and complex algorithms that often underpin AI systems. This approach is not to diminish their importance, quite the contrary. Rather, it's to ensure that we first grasp the fundamental principles, potential applications, and broader implications of AI without being encumbered or bogged down by minute technical details at the outset. By temporarily abstracting away from the mathematical underpinnings, we create space for a more intuitive understanding of AI's core concepts. This approach allows us to focus on the why and what before delving into the how. It's akin to understanding the purpose and potential of a car before examining its engine components. As we progress through this presentation, I invite you to approach these concepts with an open mind, focusing on their practical significance and potential impact. We'll explore how AI is reshaping industries, augmenting human capabilities, and opening new frontiers of possibility. Rest assured, for those eager to delve deeper into the technical aspects, we will address the underlying mathematics and algorithms in subsequent sessions. This initial high-level overview serves as a crucial foundation, providing context that will enhance your appreciation and understanding of the technical details when we do explore them. So let us begin this intellectual journey with curiosity and enthusiasm. Together we'll unravel the complexities of AI, making it accessible and true to our series title, quote unquote, easy to comprehend. Let's dive into the fascinating world of artificial intelligence, shall we? As you recall, in part one, we delved into the critical concepts of quantifying uncertainty, explored the intricacies of probabilistic reasoning, and examined how these principles apply to reasoning over time. These fundamental ideas set the stage for our continued exploration today. Part two builds upon this foundation, taking us from the theoretical realm into the practical world of decision-making. We'll begin by introducing the broad concept of decision-making in AI, then navigate through the landscape of simple decisions, exploring everything from the foundations of decision theory to advanced approaches in uncertain environments. We'll then venture into the fascinating territory of complex decisions, where we'll encounter sequential decision problems, partially observable environments, and cutting-edge applications of reinforcement learning. Our journey today will bridge the gap between the probabilistic foundations we've established and their real-world applications in AI systems. We'll see how the concepts of uncertainty quantification and probabilistic reasoning that we discussed in part one directly inform and enhance decision-making processes in various domains, from autonomous systems and medical diagnosis to strategic planning and big data analysis. As we progress through this presentation, you'll gain a holistic understanding of how modern AI systems make decisions, balancing uncertainty, multiple criteria, ethical considerations, and long-term consequences. By the end of our session, you will have a comprehensive view of the current state of AI decision-making and a glimpse into its exciting future. So let's embark on this final leg of our intellectual journey where theory meets practice and where the true power of AI in decision-making comes to life. We have an exciting array of topics ahead, and we're thrilled to have you with us as we explore the cutting edge of AI decision-making technologies. Decision-making. Introduction to decision-making. What is decision-making? Well, in a nutshell, decision-making is a fundamental cognitive process that involves selecting a course of action from multiple alternatives. In the context of AI, decision-making encompasses the ability of systems to choose actions that achieve specified goals, often while balancing multiple objectives and handling uncertainty. The importance of decision-making spans various fields. In business, is crucial for strategic planning and resource allocation. Healthcare relies on decision-making for accurate diagnosis and effective treatment planning. The finance sector uses decision-making algorithms for investing strategies and risk management. In robotics, decision-making is essential for autonomous navigation and task planning. We'll explore the spectrum of decision-making from single choices to complex, multifaceted problems. Simple decisions might involve single-stage deterministic environments with full observability. As we move towards complex decisions, we encounter multi-stage problems in stochastic, partially observable environments. Key components of AI decision-making systems include perception, that is, gathering and processing information, reasoning, aka inferring the current state and predicting future outcomes, planning, that is, gathering and evaluating sequences of actions, and learning, that is, improving decision-making capabilities over time. So, those are the key components: perception, reasoning, planning, and learning. Challenges in AI decision-making include handling high-dimensional state and action spaces, dealing with long-term consequences of actions, balancing exploration of new strategies with exploitation of known good strategies, and ensuring that AI systems make decisions that are both safe and ethically sound. As we progress through this presentation, we'll delve deeper into these concepts, exploring sophisticated approaches that enable AI systems to make increasingly complex and nuanced decisions. Foundations of decision theory. Decision theory provides the foundational framework for understanding how agents should make decisions under uncertainty. It integrates probability theory, which we explored in part 1, with utility theory to create a powerful approach for rational decision making. At the core of decision theory is the concept of rational agents that maximize expected utility. This principle states that a rational agent should choose the action that leads to the outcome with the highest expected utility. While this model provides a clear normative standard, it is important to note its limitations and critiques. particularly in modeling human behavior. Utility theory is built on a set of axioms that define rational preferences. These include completeness, that is the ability to compare all outcomes, transitivity, that is consistent preferences, continuity, that is the ability to create equivalent lotteries, and independence, that is irrelevant alternatives don't affect choice. Understanding these axioms is crucial for developing well-founded decision-making systems. Utility functions are mathematical representations of preferences. They can capture different risk attributes. For example, risk-averse, risk-neutral, or risk-seeking, and often exhibit properties like diminishing marginal utility. In complex scenarios, we may need to work with multi-attribute utility functions that balance multiple, possibly conflicting objectives. Decision trees and influence diagrams are graphical tools for representing and analyzing decision problems. They allow us to visually map out the structure of a decision, including chance events, decision points, and outcomes. The process of rolling back a decision tree helps identify the optimal sequence of decisions. While decision theory provides a powerful framework, applying it in practice comes with challenges. These include accurately eliciting utilities from stakeholders, accounting for the cognitive limitations of real decision makers, that is, bounded rationality, and incorporating ethical considerations into the decision-making process. As we move forward, we'll see how these foundational concepts are applied and extended in various decision-making scenarios, from simple choices to complex sequential decision problems. Multi-criteria decision-making methods. MCDM is the acronym for multi-criteria decision-making. These methods have gained significant attention in the past decade, as highlighted by a 2021 paper by Kashavas et al. In a comprehensive survey talking about all these different methods. These methods provide a systematic approach to complex decision problems where multiple, often conflicting criteria must be considered simultaneously. We'll explore several popular MCDM methods, each with its unique approach to synthesizing multiple criteria into a single decision. AHP, the analytic hierarchy process, decomposes complex problems into a hierarchy, using pairwise comparisons to establish priorities, and includes a consistency check to ensure reliable judgments. TOPSIS, which is the acronym for Technique for Order Preference by Similarity to Ideal Solution. TOPSIS identifies the best alternative as the one closest to the ideal solution and furthest from the negative ideal solution, providing a clear rationale for the final ranking. PROMETHI, which is an acronym for Preference Ranking Organization Method for Enrichment Evaluations, quite a mouthful. PROMETHI uses outranking relations and preference functions to compare alternatives, offering flexibility in how differences between alternatives are evaluated. ELECTRA, short for Elimination and Choice Expressing Reality, which is another outranking method that uses concordance and discordance indices to establish the strength of preference for one alternative over another. VICA, which is an acronym for Multi-Criteria Optimization and Compromise Solution, focuses on ranking and selecting from a set of alternatives in the presence of conflicting criteria, emphasizing closeness to the ideal solution. These methods find applications across various fields. In supply chain management, they're used for supplier selection and logistics optimization. Energy planners use MCDM for selecting renewable energy projects. Environmental managers apply these techniques for sustainability assessments. In healthcare, MCDM aids in evaluating treatment options, and there are plenty of other examples that we can cite. Looking to the future, we see trends towards integrating MCDM with artificial intelligence and machine learning, handling big data in decision-making processes, addressing group decision-making and consensus building, and developing fuzzy and intuitionistic fuzzy methods. MCDM methods to better handle uncertainty and vagueness in decision criteria. As we progress, we'll see how these MCDM methods can be combined with other decision-making techniques to address increasingly complex real-world problems. Let's look at more types of uncertainty and what existing papers out there talking about them or providing us with more information. Decision-making under uncertainty. Montebello and von Winterfeld wrote a 2015 paper that emphasizes the importance of understanding uncertainty in decision-making. They distinguish between aleatory uncertainty, which arises from inherent randomness in the system, and epistemic uncertainty, which stems from a lack of knowledge. Remember these two kinds of uncertainty that we went through in part 1. Aleatory uncertainty is typically modeled using probability distributions. Examples include weather patterns and stock market fluctuations. Epistemic uncertainty, on the other hand, often requires approaches like Bayesian inference or fuzzy logic to represent our lack of knowledge about parameters or model structures. To address these uncertainties, decision makers can employ various approaches. Probability theory, particularly Bayesian decision theory, provides a rigorous framework for reasoning under uncertainty. Fuzzy set theory allows for dealing with vague or imprecise information using concepts like fuzzy numbers and linguistic variables. Robust decision-making techniques such as minimax criteria and scenario planning aim to find solutions that perform well across a range of possible future scenarios. The decision analysis process typically involves several steps: structuring the problem, quantifying uncertainties, eliciting preferences, and performing sensitivity analysis to understand how changes in assumptions affect the final decision. It's crucial to consider the behavioral aspects of decision-making under uncertainty. Prospect theory, developed by Kahneman and Tversky, explains phenomena like risk aversion and loss aversion. Cognitive biases, such as anchoring and the availability heuristic, can significantly impact decision-making. Framing effects demonstrate how the presentation of a problem can influence the decision outcome, for sure. Advanced techniques like info-gap decision theory, possibility theory, and Dempster-Shafer theory offer alternative frameworks for handling uncertainty, each with its own strengths in dealing with different types of unknown or partially known information. Understanding these concepts and techniques is essential for developing AI systems that can make robust decisions in the face of real-world uncertainties. Multi-attribute utility theory addresses situations where decisions depend on several distinct attributes of outcomes. This is common in real-world decision-making, where multiple factors must be considered simultaneously, often with conflicting objectives and incommensurable units of measurement. Several techniques exist for combining multiple attributes into a single utility function. Additive utility functions, the simplest form, assure that attributes contribute independently to overall utility. Multiplicative utility functions can handle some interactions between attributes, while multilinear utility functions offer the most general form, but at the cost of increased computational complexity. Stochastic dominance is a particularly useful concept in multi-attribute decision-making, especially when dealing with uncertainty. First-order stochastic dominance allows for unambiguous comparison of alternatives when one alternative is preferable for every possible outcome. Second-order stochastic dominance is weaker, but still provides valuable insights, especially in financial decision-making. Eliciting multi-attribute utility functions from decision makers is a crucial and challenging task. Methods include direct assessment, where decision makers directly specify their preferences. Indifference methods, which find points of equal preference, and gamble method, which use hypothetical lotteries to reveal preferences. Challenges in multi-attribute decision-making include properly scaling and normalizing attributes, dealing with uncertainty across multiple attributes simultaneously, and accounting for cognitive limitations in assessing multiple attributes. Applications of multi-attribute utility theory are wide-ranging. In policy analysis and public decision-making, it helps balance diverse societal needs. Engineering design optimization uses these techniques to find optimal solutions considering multiple performance criteria. Personal decision support systems can employ multi-attribute utility theory to help individuals make complex life decisions. As we move forward, we'll see how these concepts integrate with other decision-making techniques to address increasingly complex real-world scenarios. Now, before we move on to the next slide, I want to make a simple statement, and that is, we have gone through both part 1 and part 2 that so far, we have gone through a lot of different concepts with a lot of terms that you may not immediately know what they are in depth. It's okay, because I don't expect the audience to know everything already, and this is sort of like an overview. And I don't expect the audience to actually be very knowledgeable in everything that we talked about here. But the goal of this presentation is to give the audience an initial look into all the different terms and the basic concepts so that you can dive into any of these deeper, in a deeper level, read the papers that I provide you as references, and then you will gradually go to the next step and get more and more about more deep into the concepts. And then when you need to implement them, then you get into the formulas and mathematical algorithms and such. So don't worry if you don't get everything that's said here, because that's not the purpose that you expect you to get everything here. But if you can get even 30% and have an idea about what AI involves, or all of these things that AI is like an army Swiss knife, where all these tools are around to make AI smart, right? So keep that in mind for those who may not have a full view of all the terms. It's totally okay. So let's get back to the next slide, decision networks. Decision networks provide a powerful formalism for expressing and solving decision problems. They are a natural extension of Bayesian networks, which we already explored in part 1, adding decision and utility nodes to the probabilistic framework. The structure of a decision network consists of 3 types of nodes. Chance nodes, representing random variables. Decision nodes, representing points where the decision maker must choose an action. And utility nodes, representing the value or desirability of outcomes. So 3 types of nodes. As an extension of Bayesian networks, decision networks inherit the ability to compactly represent complex probabilistic relationships. They go further by incorporating actions and their consequences, allowing for the modeling of sequential decision-making processes. Dynamic decision networks extend this to handle temporal aspects of decision problems. Several algorithms exist for inference in decision networks. Variable elimination can be adapted from Bayesian networks to compute optimal decisions. For larger, more complex networks, Monte Carlo methods provide approximate solutions. We talked about Monte Carlo in part 1 and also in the previous AI Made Easy presentations. You can look them up if you want to review it. The decision network representation offers several advantages. It provides a compact way to represent complex decision problems, explicitly models dependencies between variables, and facilitates sensitivity analysis to understand how changes in model parameters affect optimal decisions. However, challenges exist. Of course, challenges exist. As you can imagine, in using decision networks for real-world problems. What are they? First is scalability. Scalability can be an issue for large, complex problems. Eliciting accurate probabilities and utilities from domain experts or data can also be difficult. Handling continuous variables and decision spaces also presents computational challenges. Despite these challenges, decision networks find applications in various domains. In medicine, they are used for diagnosis and treatment planning. Businesses use them for strategy formulation and risk management. Environmental policymakers employ decision networks to evaluate the potential impacts of different policies. As we progress, we'll see how decision networks can be integrated with other techniques to handle increasingly complex decision scenarios, particularly in partially observable environments. Value of information. The value of information is a pretty crucial concept in decision theory. Quantifying the expected improvement in decision quality that could be obtained by acquiring additional information before making a decision. This concept is particularly useful for guiding the process of information gathering prior to making a final decision. We distinguish between the value of perfect information, which assumes complete resolution of uncertainty, and the value of imperfect information, which considers more realistic scenarios where new information reduces but does not eliminate uncertainty. That's what happens in the real world. Several measures are used to calculate the value of information. The expected value of perfect information, EVPI in short, represents the upper bound on how much a decision maker should be willing to pay for information. The expected value of sample information, EVSI, quantifies the value of specific pieces or sources of information. The expected value of including uncertainty, EVRU, measures the importance of explicitly considering uncertainty in the decision process. So those are parameters actually giving you a glimpse of, if you have to get into the algorithms, those are the key parameters that you would need to do any kind of calculations in the context of acquiring information, evaluating information, whether how valuable it is. So value of information analysis finds applications in various fields. In medicine, it guides decisions about which diagnostic tests to perform. Market researchers use it to determine the worth of consumer surveys of product trials. Environmental scientists apply it to optimize monitoring strategies and resource exploration. One of the key challenges is balancing the costs of acquiring information against its potential benefits. This leads to the development of information acquisition strategies, methods for sequential information gathering, and stopping rules to determine when enough information has been collected. In machine learning, the value of information concept is closely related to active learning and optimal experiment design. It also plays a key role in the exploration-exploitation trade-off in reinforcement learning. Challenges in applying value of information analysis include computational complexity in large decision spaces, handling dependencies between different sources of information, and incorporating decision makers' risk attributes into the valuation process. Advanced concepts include considering the value of information in group decision-making contexts, analyzing the dynamic value of information in sequential decision problems, and studying how the value of information changes in adversarial or competitive settings. Understanding and applying the value of information concept is essential for developing AI systems that can efficiently gather and utilize information to improve decision quality. Ethical decision making, and we're going to use the example autonomous systems. As autonomous systems become more prevalent, ethical decision making becomes crucial. Miller, in a 2016 paper, discusses the AV ethics project, AV aerial vehicle ethics project, which addresses ethical challenges in autonomous vehicles. AV is autonomous vehicles, pardon me, not aerial vehicle. I meant autonomous vehicles. This project serves as a microcosm for the broader challenges of implementing ethical decision-making in AI systems. Programming ethical decisions into AI systems presents several challenges. We must find ways to formalize ethical principles in a way that machines can understand and apply. This often involves dealing with ethical dilemmas and trade-offs where there may not be a clear right answer. Moreover, ethical standards can vary across cultures and contexts, adding another layer of complexity. The Autonomous Vehicle Ethics Project explores these issues in the context of self-driving cars. It is a pretty interesting read, not a heavy reading, where you have to digest a formula and stop for 2 minutes before moving on from one sentence to another, but this is an interesting read. It talked about things like, for example, how should a self-driving car decide between protecting its passengers or minimizing overall harm in an unavoidable accident. The project's findings have implications beyond autonomous vehicles. extending to AI systems in healthcare, finance, and other critical domains. A key aspect of ethical AI is balancing utilitarian approaches, which aim to maximize overall good, with ontological principles, which adhere to moral rules regardless of consequences. Many researchers advocate for hybrid approaches that combine elements of both ethical frameworks. Various ethical frameworks have been proposed for AI decision-making, from Asimov's laws of robotics to more recent guidelines like the IEEE Ethically Aligned Design and the EU Guidelines for Trustworthy AI. Lots of work is going on in the trustworthy AI area. These frameworks provide a starting point for implementing ethical considerations in AI systems. Very interesting area to be involved in. Technical approaches to ethical AI include value alignment techniques, which aim to ensure AI systems act in accordance with human values. Inverse reinforcement learning, which can be used to infer ethical preferences from human behavior, and formal verification methods to ensure AI systems respect ethical constraints. Case studies such as the trolley problem in autonomous vehicles, the use of AI in criminal justice, and ethical considerations in medical AI highlight the complexity and real-world importance of these issues. Looking to the future, we must grapple with questions of moral uncertainty in AI systems, how to handle evolving ethical standards, and the need for global governance of AI ethics. As AI systems become more advanced and ubiquitous, ensuring that they make ethical decisions will be crucial for their acceptance and beneficial integration into society. Here's another example application for decision-making using AI. Medical diagnosis. On a 2020 paper by Azar and Al-Matwali, that paper reviewed decision-making methods in medical diagnosis, highlighting the complexities involved. Medical professionals often face decisions with high stakes and incomplete information, making this field an ideal application area for advanced decision-making techniques. The challenges in medical decision-making are numerous. There's inherent uncertainty in diagnosis and treatment outcomes due to the complexity of human physiology and disease processes. Time pressure in emergency situations adds another layer of difficulty. Moreover, ethical considerations and patient preferences must be taken into account, making medical decisions not just a matter of pure data analysis. AI-assisted diagnostic tools have shown great promise in addressing these challenges. Machine learning algorithms, particularly deep learning, have achieved remarkable results in analyzing medical images for radiology and pathology. Natural language processing techniques help extract valuable information from clinical notes and vast medical literature. Expert systems and clinical decision support systems aid physicians by providing evidence-based recommendations. A key strength of AI in medical diagnosis is its ability to integrate multiple data sources. Electronic health records provide a wealth of patient-specific information. Genomic and proteomic data offer insights into individual disease susceptibility and treatment responses. Data from wearable devices and IoT sensors allow for continuous patient monitoring. Population health data and epidemiological models provide context for individual diagnosis. Various methods are employed in medical decision-making systems. I can suggest a few. First one is rule-based systems use if-then rules derived from clinical guidelines. They're interpretable and can easily incorporate expert knowledge, but may struggle with uncertainty and scalability. The next method I have it here as example is fuzzy logic systems. Fuzzy logic systems are well suited to handling the imprecision inherent in medical data and knowledge. They're particularly useful in patient monitoring and control systems. Next one is artificial neural networks, especially deep learning models, excel at complex pattern recognition tasks. They've already shown impressive results in medical imaging and signal processing, but can lack interpretability. The last one example would be support vector machines. They are quite effective for high-dimensional data analysis, finding applications in genomics and proteomics. Oh, what's proteomics? The word proteomics is a combination of protein and genomics. I believe that's how it came about, proteomics. It refers to the large-scale study of proteins, particularly their structures and functions. This field of study aims to understand a few things. The entire set of proteins produced or modified by an organism or system, how these proteins interact with each other, and how they change under different conditions or in different states of health and disease. That's a little tidbit to tell you what proteomics is, in case you're not too familiar with it. So I cited 4 different methods. When we compare these methods, various performance metrics are considered, including accuracy, sensitivity, specificity, and area under the ROC curve. It's crucial to balance between performance aspects and validate results through clinical trials. Ethical and practical considerations are paramount in medical AI, as you can imagine. Explainability and transparency of AI diagnosis are essential for building trust with both healthcare providers and patients. Questions of liability and responsibility in AI-assisted decisions must be addressed. Successfully integrating AI tools into clinical workflows and ensuring healthcare professionals are adequately trained in AI capabilities and limitations are ongoing challenges. As AI continues to advance, its role in medical decision-making is likely to grow, potentially revolutionizing healthcare delivery and improving patient outcomes. In many real-world scenarios, it's impossible to specify the human's utility function completely and correctly. This uncertainty about human preferences poses significant challenges for AI systems designed to make decisions on behalf of or in collaboration with humans. This brings to our next topic, uncertainty in human preferences. Sometimes we don't even know what we would like, or our likes change every so often that we ourselves get confused. So the challenges in specifying complete utility functions stem from the complexity of human values and goals, which can be multifaceted and sometimes contradictory. Preferences are often context dependent, changing based on circumstances or framing. Moreover, human decision-making frequently exhibits inconsistencies and apparent irrationality, further complicating the task of modeling preferences. The implications of preference uncertainty are profound for AI system design and behavior. AI systems must be robust and adaptable, capable of operating effectively even when human preferences are not fully known or may change over time. This uncertainty has significant implications, particularly when the machine has the opportunity to acquire more information about human preferences. A key insight is that uncertainty about preferences ensures that the machine defers to the human, even to the point of allowing itself to be switched off. This principle is crucial for designing AI systems that respect human autonomy and values. It suggests that in scenarios where the stakes are high and preferences are uncertain, AI systems should be designed to seek human input or oversight. It's a must. Various models have been developed to handle uncertain preferences. Probabilistic utility models represent preferences as probability distributions over possible utility functions. Bayesian preference learning approaches update beliefs about preferences based on observed choices. Multi-armed bandit formulations treat preference elicitation as an exploration-exploitation problem. Techniques for handling preference uncertainty include active preference learning, where the system actively queries the user to refine its understanding of preferences. Inverse reinforcement learning, which infers preferences from observed behavior. And robust decision-making approaches that aim to perform well across a range of possible preference structures. Ethical considerations are paramount when dealing with uncertain preferences. The value alignment problem, ensuring AI systems act in accordance with human values, becomes even more challenging when those values are not fully known. Issues of fairness and bias must be carefully considered in preference modeling. Privacy concerns also arise in the process of preference elicitation and modeling. Applications of these concepts can be found in recommender systems that must make suggestions with limited knowledge of user preferences, personalized healthcare decision support systems that balance medical best practices with individual patient preferences, and autonomous systems that must interact safely and effectively with humans whose preferences may be partially unknown or changing. As AI systems become more advanced and are deployed in increasingly complex and high-stakes environments, understanding and appropriately handling uncertainty in human preferences will be crucial for their safe and beneficial integration into society. Advanced approaches in decision-making under uncertainty. Shi et al. On a 2020 paper provides a quasi-view of advanced approaches in decision-making under uncertainty. These techniques represent the cutting edge of our ability to make robust decisions in complex, uncertain environments. Quasi-Monte Carlo methods use low discrepancy sequences to provide more efficient sampling compared to standard Monte Carlo methods. This approach is particularly valuable in high-dimensional integration problems, which are common in complex decision scenarios. By providing more uniform coverage of the sample space, quasi-Monte Carlo methods can achieve faster convergence and more accurate estimates. Scenario-based decision-making involves generating a set of representative representative future scenarios, and optimizing decisions to perform well across this set. This approach is particularly useful when dealing with deep uncertainty, where probability distributions for future states are unknown or disputed. Adaptive scenario generation techniques allow for refining the scenario set as new information becomes available. Real options analysis provides a framework for valuing flexibility in decision making. This approach, borrowed from financial options theory, is particularly useful in investment and project management contexts, where the ability to adapt to changing circumstances has significant value. It allows decision makers to quantify the value of keeping options open in uncertain environments. Portfolio approaches, extending beyond modern portfolio theory, provides strategies for balancing risk and return in decision making. These techniques, originally developed for financial investments, have found applications in various fields where diversification can lead to more robust outcomes. These advanced approaches find applications across various domains in finance. They are used for derivative pricing and risk assessment. Energy planners use them to design robust systems in the face of climate uncertainty. Environmental managers apply these techniques to ecosystem management problems with uncertain dynamics. Advanced probabilistic modeling techniques complement these decision-making approaches. Gaussian processes provide a flexible framework for uncertainty quantification. Copulars allow for modeling complex dependencies between variables. Bayesian deep learning combines the power of deep neural networks with principled uncertainty quantification. However, these advanced techniques often come with significant computational challenges. Parallel and distributed computing approaches are often necessary to tackle large-scale problems. Approximation algorithms provide tractable solutions to otherwise intractable problems. Online and anytime algorithms allow for dynamic decision-making in time-sensitive situations. As we move into increasingly complex decision environments, these advanced approaches will play a crucial role in developing AI systems capable of making robust and effective decisions under uncertainty. Sequential decision problems and Markov decision processes. Sequential decision problems in stochastic environments, also known as Markov decision processes, MDPs, are fundamental to many real-world scenarios. MDPs provide a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision maker. The key components of an MDP are states, actions, transitions, and rewards. The Markov property, which states that the future is independent of the past given the present, is a crucial assumption that simplifies the model while still capturing many real-world dynamics. The transition model specifies the probabilities of moving from one state to another given an action. This can be stochastic, reflecting the uncertainty in the environment, or deterministic in simpler cases. For large state spaces, factored representations can make the model more manageable. The reward function defines the immediate payoff for taking an action in a given state. The design of this function is crucial as it shapes the behavior of the agent. In many cases, we're interested in maximizing long-term rewards rather than immediate payoffs. The utility of a state sequence is typically defined as the sum of all rewards over the sequence. In infinite horizon problems, where the decision process continues indefinitely, we often use discounted cumulative reward to ensure the sum coverages. The choice of discount factor can significantly impact the optimal policy, with higher discount factor encouraging more far-sighted behavior. The Bellman equation, a key result in dynamic programming, provides a recursive formulation of the value function. The principle of optimality is the foundation for many MDP solving algorithms. MDPs find applications in various domains. In inventory management, they can optimize stocking decisions. In healthcare, MDPs can guide treatment planning and resource allocation. Robotics uses MDPs for path planning and task scheduling. In finance, they are applied to portfolio management and trading strategies. Extensions of the basic MDP framework include partially observable MDPs, POMDPs, POMDPs, and POMDPs, as I like to call it, for situations where the state is not fully observable. Constrained MDPs for incorporating safety constraints, and multi-agent MDPs for modeling decentralized control problems. Understanding MDPs is crucial for developing AI systems capable of making sequences of decisions in uncertain environments, forming the foundation for more advanced reinforcement learning techniques. Solving Markov decision processes. Again, Markov decision processes, in short, is MDPs. MDPs is a fundamental problem in AI and operations research. The goal is to find an optimal policy that maximizes the expected cumulative reward over time. A policy in an MDP is a mapping from states to actions, telling the agent what to do in each situation. While we often focus on deterministic policies, stochastic policies can be useful in certain scenarios, especially in partially observable or multi-agent settings. Interestingly, for any MDP with full observability, there always exists an optimal policy that is both deterministic and stationary, that is not dependent on history. Two classic algorithms for solving MDPs are value iteration and policy iteration. Value iteration works by iteratively improving estimates of the value function using the Bellman equation. It's simple to implement but can be slow to converge. Policy iteration alternates between policy evaluation, that is computing the value function for the current policy, and policy improvement, that is finding a better policy based on the current value function. While it often converges in fewer iterations, each iteration can be more computationally expensive. Linear programming offers an alternative approach to solving MDPs, particularly useful for constrained MDPs where additional restrictions are placed on the policy. For large state spaces, exact solutions become intractable, and we turn to approximate methods. Approximate dynamic programming uses function approximation to represent the value function compactly. Temporal difference learning provides a way to learn from experience without a complete model of the environment. Online planning methods like Monte Carlo tree search, MCTS, and its variants have shown remarkable results or success in complex domains like Go and video games. These methods interleave planning and execution, focusing computational effort on the most promising paths. Hierarchical approaches, such as the options framework and hierarchical abstract machines, HAMs in short, provide ways to decompose complex problems into more manageable subproblems. This can dramatically speed up learning and planning in large MDPs. Dealing with large or continuous state and action spaces presents additional challenges. State aggregation, factored representations, and functional approximation methods are common approaches to managing this complexity. Finally, many real-world problems involve multiple, possibly conflicting objectives. Multi-objective MDPs extend the framework to handle these scenarios, often using concepts like Pareto optimality to reason about trade-offs between different goals. Understanding these solution methods is crucial for applying MDPs to real-world problems and forms the basis for more advanced reinforcement learning techniques. Partially observable Markov decision processes, POMDPs. POMDPs represent a more challenging class of problems where the agent doesn't have full information about its current state. This partial observability is common in real-world scenarios, making POMDPs a powerful framework for modeling complex decision-making under uncertainty. The key concept in POMDPs is the belief state, which is a probability distribution over possible states. As the agent acts and receives observations, it updates its belief state using Bayes' rule. This leads to a continuous belief space, even if the underlying state space is discrete. Solving POMDPs is notoriously difficult due to the curse of dimensionality and the curse of history. One approach is to convert the POMDP to a continuous space MDP over belief states. However, the belief MDP is generally intractable to solving exactly. Value iteration in belief space is a fundamental approach to solving POMDPs. The value function over beliefs can be represented as a set of alpha vectors and corresponding to a policy tree. Pruning techniques are crucial for managing the computational complexity of this representation. Point-based value iteration algorithms improve efficiency by focusing on reachable belief states. These methods sample beliefs and perform backups only at these points, dramatically reducing computational requirements while still providing good approximations. Policy iteration for POMDPs often uses finite state controllers as a compact policy representation. Bounded policy iteration algorithms provide ways to incrementally improve these controllers. For large POMDPs, approximate methods become necessary. Monte Carlo sampling approaches can estimate value functions and policies. Particle filtering provides an efficient way to maintain and update belief states. Recent advances in deep reinforcement learning have also been applied to POMDPs with promising results. A key aspect of optimal behavior in POMDPs is the importance of information gathering. Actions that reduce uncertainty about the state can be valuable, even if they don't provide immediate rewards. This leads to a natural exploration-exploitation trade-off in POMDP policies. POMDPs find applications in various domains. In robotics, they are used for simultaneous localization and mapping, which is SLAM, and navigation under uncertainty. Healthcare uses POMDPs for medical diagnosis and treatment planning with imperfect information. In finance, POMDPs can model portfolio management with hidden market states. Autonomous driving systems use POMDPs to make decisions with limited sensor information. So understanding POMDPs and their solution methods is crucial for developing AI systems that can operate effectively in a partially observable, uncertain environments that characterize many real-world problems. Decision theoretic agents for POMDP environments. A decision theoretic agent for POMDP, again, POMDP is short for partially observable Markov decision processes. So for POMDP environments, a decision theoretic agent uses a dynamic decision network to represent transition and sensor models. This network helps the agent update its belief state and project forward possible action sequences, allowing it to make informed decisions even in the face of partial observability and uncertainty. The structure of such an agent typically includes three main components: a belief state maintenance module, a policy execution module, and a learning and adaptation module. The belief state maintenance module is responsible for updating the agent's beliefs about the world state based on actions taken and observations received. The policy execution module decides on actions based on the current belief state, while the learning and adaptation module allows the agent to improve its performance over time. Dynamic decision networks extend the concept of Bayesian networks to sequential decision-making problems. They provide a compact way to represent the relationships between actions, observations, and utilities over time. By rolling up these networks, we can perform multi-step planning, considering the long-term consequences of actions. Belief state updates are a crucial part of the agent's reasoning process. While exact updates using Bayes' rule are possible for small problems, approximate methods like particle filters or Gaussian approximation are often necessary for larger or continuous state spaces. Action selection in POMDPs can be challenging due to the need to reason about both the immediate rewards and the value of information gained by actions. Myopic policies that maximize immediate expected utility are simple, but often suboptimal. Look-ahead policies that consider future sequences can perform better, but are more computationally expensive. Monte Carlo tree search adapted to belief space provides a flexible approach to balancing these concerns. Online POMDP algorithms are crucial for agents that need to make decisions in real time. These include real-time dynamic programming approaches, forward search in belief space, and anytime algorithms that can provide improving solutions under time constraints. Learning plays a vital role in POMDP environments where the true model may not be known in advance. Model-based approaches attempt to learn the transition and observation models, while model-free approaches directly optimize the policy. Bayesian reinforcement learning provides a principled way to balance exploration and exploitation in these uncertain environments. Now let's transition to complex decision making. As we transition from simple to complex decisions, we encounter scenarios characterized by multiple interconnected factors, conflicting objectives, and long-term consequences. These complex decisions often involve strategic planning and resource allocation, as well as navigating uncertainty on a larger scale than we've previously discussed. The emergence of big data and artificial intelligence has both enabled and necessitated more sophisticated, complex decision-making techniques. The exponential growth in available data, coupled with advancements in machine learning and increased computational power, has opened up new possibilities for decision support systems. However, it has also introduced challenges. in terms of data management, interpretation, and the need for robust, scalable algorithms. Traditional decision-making methods often fall short when dealing with the complexity of modern problems. There's a growing need for advanced techniques that can integrate human expertise with AI capabilities, handle uncertainty and incomplete information at scale, and adapt to dynamic, evolving environments. Cognitive challenges play a significant role in complex decision-making. Concepts like bounded rationality and cognitive biases highlight the limitations of human decision-making in complex environments. Information overload and decision fatigue are increasingly common problems, necessitating better tools and strategies for managing complexity. Ethical considerations become even more critical as AI systems take on more complex decision-making tasks. Issues of transparency, explainability, fairness, and accountability must be addressed to ensure that these systems are trustworthy and aligned with human values. Interdisciplinary approaches are crucial for tackling complex decision problems. Combining insights from computer science, psychology, and domain-specific expertise can lead to more holistic and effective solutions. The concept of human AI teaming is emerging as a powerful paradigm. This is human AI teaming is the concept and the term. And that is emerging as a powerful paradigm for leveraging the strengths of both human intuition and AI's data processing capabilities. Emerging paradigms in complex decision-making include adaptive and learning-based systems that can improve their performance over time, decentralized and multi-agent approaches for handling distributed problems, and sophisticated human-AI collaboration frameworks. As we move forward in our discussion, we'll explore how these concepts are applied in various domains, from reinforcement learning for combinatorial optimization to AI-driven decision-making in the era of big data. Understanding these advanced approaches is crucial for developing AI systems capable of making effective decisions in the complex, uncertain environments that characterize many real-world problems. There's a paper from Myafkina et al. Again, I'm sure I mispronounced that word, but forgive me. This is a paper, they call it a survey, about reinforcement learning techniques for combinatorial optimization problems, which are quite central to many complex decision-making scenarios. Combinatorial optimization involves finding optimal solutions from a finite set of possibilities, such as route planning, resource allocation, or portfolio optimization. Reinforcement learning approaches have shown promising results in tackling these challenges. Q-learning, a value-based method, can be adapted to handle large-scale or large state spaces through function approximation techniques. Policy gradient methods like reinforce, all in capital letter, that is one of the methods called reinforce, and actor-critic architectures directly optimize the policy. So if you have not heard of these terms, just first time I want to familiarize these terms with you so that you can maybe look them up and learn more about them later. Okay, so I was on policy gradient methods like reinforce or actor-critic architectures. Those are methods that directly optimize the policy, which can be advantageous in high-dimensional action spaces. Monte Carlo tree search, famously used in AlphaGo, provides a powerful framework for balancing exploration and exploitation in complex decision spaces. Applying RL is reinforcement learning, to combinatorial optimization comes with several challenges. The state and action spaces are often extremely large and complex. Rewards may be sparse and delayed, making it difficult to learn effective policies. Generalization across different problem instances is also a significant challenge, as we want our algorithms to perform well on unseen problems. Advanced RL, advanced reinforcement learning techniques, are being developed to address these challenges. Attention mechanisms and transformers, originally from natural language processing, have been adapted to handle the sequential nature of many combinatorial problems. Graph neural networks provide a natural way to work with the structured data common in combinatorial optimization. Meta-learning approaches aim to learn algorithms that can quickly adapt to new problem instances. And there are hybrid approaches. These hybrid approaches combining RL, reinforcement learning, with traditional optimizational techniques show particular promise. These methods can leverage the strengths of both paradigms, using RL, reinforcement learning, to guide high-level decision-making while employing exact solvers or heuristics for low-level optimization. Benchmarking and evaluation of RL approaches for combinatorial optimization is crucial. Comparisons with state-of-the-art exact and heuristic methods provide insight into the strengths and weaknesses of RL approaches. Generalization to larger problem sizes and computational efficiency are key considerations in practical applications. Looking to the future, we see exciting directions such as quantum-inspired RL algorithms that may offer advantages for certain types of combinatorial problems. There's also a growing focus on explainable RL, explainable reinforcement learning, which is crucial for building trust in these systems, especially in high-stakes decision-making scenarios. Integration with human expertise and domain knowledge remains an important area of research, as human insights can often complement and enhance RL approaches. As we continue to develop these techniques, RL for combinatorial optimization has the potential to revolutionize how we approach complex decision-making problems across a wide range of industries and applications. Strategic planning and complex decision-making. There is a paper, again, I use these papers to point out some of these key points, because then you can go and look at those papers. They're listed at the end of this presentation. Sommers et al. On a 2020 paper present a case study of a Greek company facing complex decisions without effective strategic planning. This study highlights the challenges of making decisions in a rapidly changing business environment without a clear long-term strategy. So what best way to demonstrate the need for complex decision-making using AI, but to take a look at a case study, a real case study. So this paper is a very interesting one. Strategic planning is crucial for organizations to set long-term visions that align resources and capabilities, and also adapt to changing environments. The case study illustrates how the absence of strategic planning can lead to ad hoc decision making, which is not a good thing. Ad hoc, that means you haven't really given thought to all the areas that you need a lot of thinking, think through. And this kind of ad hoc decision making often results in suboptimal outcomes and missed opportunities. Key opponents of strategic decision making include environmental scanning to understand the context in which the organization operates, scenario planning to prepare for different possible futures, resource allocation to ensure efficient use of limited resources, and risk assessment to identify and mitigate potential threats. Various tools and frameworks assist in strategic planning. The Balanced Scorecard provides a holistic way of organizational performance. Blue Ocean Strategy focuses on creating uncontested market spaces. Porter's 5 Forces analysis helps understand the competitive landscape. Pestel spells P-E-S-T-E-L, analysis examines macro-environmental factors affecting the organization. So those are some of the tools that can help you to examine strategy and then do some long-term planning. The integration of AI in strategic planning is an emerging trend. Big data analytics can provide deep market insights, predictive modeling can forecast trends, and AI-assisted scenario generation can help evaluate a wide range of possible futures. However, strategic decision-making faces several challenges. Dealing with uncertainty and ambiguity is inherent in long-term planning. Balancing short-term pressures with long-term goals can be difficult, especially in volatile environments. Managing diverse stakeholder expectations and potential conflicts adds another layer of complexity. The case study provides several lessons and best practices. It underscores the importance of a systematic approach to decision-making, emphasizing the need for continuous monitoring and adaptation of strategies. Fostering a culture of strategic thinking throughout the organization is crucial for effective implementation. Emerging trends in strategic planning include the adoption of agile and adaptive planning methodologies to respond quickly to changes, collaborative and participatory strategy formulation to leverage diverse perspectives, and the integration of sustainability and social responsibility considerations into strategic decisions. This case study and the broader discussion of strategic planning underscore the need for organizations to invest in strategic planning capabilities to navigate complex decision landscapes effectively. As AI and data analytics continue to evolve, their integration into strategic planning processes offers exciting possibilities for more informed and robust decision-making in complex, uncertain environments. Explainable AI in autonomous systems. Here I want to cite another paper that can illustrate the topic at hand, that what we're going to talk about. This paper was by Liu et al. 2021 paper where Liu explored the role of explainable AI, XAI in short, X as in explainable, XAI, and explainable AI, the role of explainable AI in increasing user trust in autonomous systems. This is what this paper talks about, explore what this topic is all about. As AI systems make increasingly complex decisions, it's crucial to understand and explain their reasoning. especially in high-stakes domains like autonomous vehicles, healthcare, and finance. The importance of transparency in AI decision-making cannot be overstated. It builds trust with users and stakeholders, ensures compliance with emerging regulations, and provides valuable insights for debugging and improving AI systems. In autonomous systems where AI makes critical real-time decisions, explainability becomes even more crucial for safety and accountability. Several XAI techniques have been developed to address this need. LIME, L-I-M-E, which is short for Local Interpretable Model Agnostic Explanations, quite a mouthful, LIME in short, provides explanations for individual predictions by approximating complex models with simpler interpretable ones around specific data points. Another one called SHAP, S-H-A-P, which stands for Shapley Additive Explanations, uses game theory concepts to assign importance values to each feature of a particular prediction. The next one I want to introduce is called LRP, which stands for Layer-Wise Relevance Propagation. Layer-wise relevance propagation, LRP, is particularly useful for deep neural networks, visualizing which input features contributed most to a decision. Counterfactual explanations offer actionable insights by showing how input changes would affect the outcome. In autonomous systems, these techniques find various applications. For self-driving cars, XAI, explainable AI, can explain driving decisions, helping passengers understand why the car chose a particular route or made a specific maneuver. In autonomous robots, it can clarify task prioritizations, making it easier for human operators to supervise and collaborate with the system. For unmanned aerial vehicles, XAI can justify navigation choices, which is crucial for both operators and regulators. Implementing XAI in autonomous systems comes with several challenges. There's often a trade-off between the fidelity of explanations to the original model and their interpretability to humans. High-dimensional and complex decision spaces common in autonomous systems can be difficult to explain concisely. Additionally, generating explanations in real time, as required in many autonomous systems, presents computational challenges. Evaluating XAI systems is itself a complex task. Matrices uses to consider the faithfulness of explanations to the original model, their comprehensibility to non-expert users, and the actionability of the insights provided. The human-AI interaction aspect of explainable systems is crucial. Interactive explanations allow users to query the system for more details. Adaptive explanations can adjust their complexity based on the user's expertise. In many cases, XAI can facilitate collaborative decision-making between humans and AI, leveraging the strengths of both. Ethical and social implications of XAI are significant. There's growing recognition of a quote-unquote right to explanation in automated decision-making, particularly in domains affecting individual rights or opportunities. However, XAI also raises privacy concerns, as detailed explanations might inadvertently reveal protected information. Looking to the future, we see exciting directions in XAI research. There's growing interest in causal explanations, which go beyond correlation to explain why AI systems make certain decisions. Explaining AI's uncertainty and confidence levels is another important area, particularly for autonomous systems operating in uncertain environments. Looking to the future, we see exciting directions in XAI research. As autonomous systems become more prevalent in our daily lives, from self-driving cars to AI-powered medical diagnostics, the need for explainable AI will only grow. XAI techniques will play a crucial role in building trust, which is very important in the whole AI movement, ensuring safety, and facilitating the seamless integration of AI into critical decision-making processes. AI for decision-making in the era of big data. There's a paper, Dewey, if that's how it's pronounced, et al., from 2021. That paper discusses the evolution of AI for decision-making, specifically in the era of big data. The sheer volume, velocity, and variety of data available today present both opportunities and challenges for decision makers. AI techniques have become essential tools for extracting insights and making informed decisions from this wealth of information. Machine learning algorithms can identify patterns and insights from vast data sets, enabling predictive analytics and automated decision-making. We have more and more data each day generated by all sorts of mechanisms. The internet, IoT devices, or mobile devices, what have you. Lots and lots of data incrementally, exponentially growing each day. Natural language processing extracts meaning from textual data, allowing for sentiment analysis and the processing of unstructured information. Computer vision techniques analyze visual information, opening up new possibilities in areas like quality control and security. However, the authors, remember the authors of this paper especially, also highlight ethical considerations, such as data privacy, algorithmic biases, and the need for human oversight. Future research directions include developing more robust and adaptable AI systems, improving interpretability, and addressing societal impacts of AI-driven decision-making. Big data analytics platforms and cloud-based AI services have democratized access to powerful decision-making tools. AutoML, you remember AutoML, which is used everywhere by Google. I think it came out in 2018, I believe. AutoML, which is automated machine learning, is making it much easier for non-experts to develop and deploy AI models for decision-making. It's like an API set, make it much easier. Industry-specific applications are numerous and transformative. In healthcare, AI is enabling personalized medicine and improving epidemic predictions. Financial institutions use AI for algorithmic trading and fraud detection. Retailers leverage AI for demand forecasting and personalized recommendations. Implementing AI-driven decision systems comes with challenges, including integration with existing processes, addressing skill gaps, and managing organizational change. However, the potential benefits in terms of efficiency, accuracy, and innovation are driving widespread adoption. Looking to the future, we see trends like edge computing enabling real-time decision-making closer to the data source, quantum computing promising breakthroughs in solving complex optimization problems, and increasingly sophisticated AI-human collaboration in decision-making processes. As we continue to navigate the big data era, AI will play an increasingly central role in how we make decisions across all sectors of society. The challenge lies in harnessing these powerful tools responsibly and effectively to create value while addressing ethical concerns and ensuring human values remain at the forefront of decision-making processes. Deep reinforcement learning in complex environment. There's another paper, 2019 paper by Arup Kumaran et al. It's a survey. It surveys the application of deep reinforcement learning in video games, which serve as complex, dynamic decision-making environments. Games like Go, StarCraft, and Dota 2. I'm not sure I know what with that game. But these games, examples like these games, have served as benchmarks for AI capabilities, demonstrating the potential of deep RL, reinforcement learning, to make complex decisions in uncertain and adversarial environments. I should have listed the papers actually on the slides itself, but I haven't done that here. But you can reference the reference slide at the end, and you will find all these different papers. The progression from simple Atari games, remember Atari games, to complex strategic or strategy games like StarCraft represents a significant leap in the complexity of environments that AI can handle. These game environments provide rich, controllable testbeds for developing and evaluating AI algorithms, often with dynamics that transfer well to real-world problems. Key algorithms in Deep RL include Deep Q networks, DQN in short, which combined Q learning with deep neural networks to achieve human-level performance on Atari games, and policy gradient methods like PPO. PPO stands for Proximal Policy Optimization, and TRPO, which stands for Trust Region Policy Optimization, which directly optimize the policy. Actor-critic architectures. Remember, we mentioned this on an earlier slide. Actor-critic architectures combining value function approximation with policy gradients have shown particular promise in complex environments. Despite these successes, Deep RL faces several challenges. Sample efficiency remains a concern, with many algorithms requiring millions of interactions to learn effective policies. Millions. Stability and reproducibility of results can be problematic, especially in complex environments. Exploration in high-dimensional spaces, high-dimensional state spaces, common in real-world problems, presents ongoing challenges. Advanced techniques are being developed to address these issues, though, right now. Lots of people are working on these problems. Meta-learning approaches aim to develop algorithms that can quickly adapt to new tasks. Hierarchical RL decomposes complex tasks into manageable subtasks. Multi-agent RL is pushing the boundaries of what's possible in collaborative and competitive scenarios. The skills developed in game environments have potential applications in real-world, complex decision-making scenarios. In robotics, techniques developed in simulated environments are being transferred to real-world systems. Resource management in large-scale systems such as data centers or power grids can benefit from RL approaches. Also, autonomous vehicles use RL for navigation and decision-making in complex traffic scenarios. Ethical considerations are paramount as we move forwards, or as we move towards deploying deep RL systems in the real world. Ensuring safety during both the exploration phase and deployment is crucial. The black box nature of deep neural networks raises concerns about transparency and explainability of learned policies. As these systems take on more decision-making roles, their potential societal impacts must be carefully considered. Looking to the future, we see exciting prospects for deep RL. Integration with symbolic AI and knowledge bases could lead to more robust and interpretable systems. Continual learning techniques will be crucial for adapting to non-stationary environments. Human-in-the-loop RL offers promising avenues for leveraging human expertise in complex decision support systems. As deep RL continues to advance, it has the potential to revolutionize how we approach complex decision-making across a wide range of domains, from robotics to autonomous systems to resource management and beyond. All right, we are on the conclusion slide. Conclusion and future outlook. As we've seen, decision-making spans a wide spectrum from single choices to highly complex, multifaceted problems. Our journey has taken us from the foundations of probability and utility theory to the cutting edge of AI and machine learning in decision support. We've explored how advances in AI, big data analytics, and cognitive science are reshaping how we approach decision-making at all levels. From the probabilistic reasoning techniques we discussed in Part 1 to the complex reinforcement learning systems we've just examined, the field of AI-driven decision-making is rapidly evolving. Emerging trends include the integration of human expertise with AI capabilities, the development of more robust and adaptable decision support systems, and a growing focus on ethical and explainable AI. We're moving towards a future where AI systems and humans collaborate seamlessly in decision processes, leveraging the strengths of both. At least that's what we would love to see it happen. Seamlessly. Collaborate seamlessly. We'll aim for that goal for sure. However, significant challenges remain. Balancing the power of automation with the need for human oversight is crucial. Handling uncertainty and incomplete information at scale continues to be a major focus of research. As we tackle ever larger and more complex problem spaces, new techniques and approaches will be needed. The importance of interdisciplinary approaches cannot be overstated. Combining insights from computer science, psychology, ethics, and domain-specific knowledge will be crucial in developing effective decision-making frameworks for our increasingly complex world. We must consider not just the technical aspects of AI systems, but also their ethical implications and societal impacts. Looking to the future, exciting research directions are emerging. Quantum computing tools are coming to the fore. Quantum computing holds promise for solving complex optimization problems that are intractable for classical computers. Neuromorphic computing may lead to more efficient and brain-like decision systems. There's also growing interest in integrating emotional intelligence into AI decision-making, recognizing the important role that emotions play in human decision processes. And of course, there's the matter of whether we can make machines consciousness. But we're not going to talk about that area, which can be a whole big can of worms. The societal implications of these advancements are profound. The nature of work and decision-making rules is likely to change significantly. Education systems will need to adapt to prepare people for a whole new world where AI is an integral part of decision-making processes. Governance and policy frameworks will need to evolve to ensure that the responsible development and deployment of AI decision systems are being considered and regulated to a certain extent. As we conclude, it's clear that the field of AI-driven decision-making is at an exciting and critical juncture. The potential benefits are enormous, but so too are the challenges and risks. It's incumbent upon all of us, researchers, practitioners, policymakers, and citizens, to engage with these issues thoughtfully and proactively. We must commit to the responsible development and deployment of AI decision-making or AI decision systems, balancing innovation with ethical considerations. Continued research into robust, transparent, and ethical AI is essential. And perhaps most importantly, we must foster interdisciplinary collaboration and open dialogue to ensure that as we advance the capabilities of AI in decision-making, we do so in a way that benefits all of humanity. I want to thank you all for joining us on this exploration of decision-making in the modern era. The future of AI-driven decision-making is in our hands, and it's really up to all of us to shape it wisely and responsibly. This concludes our presentation on decision-making in the modern era, from simple to complex. And thank you for your attention. And before we go, we have, I think, one slide. There are these technical papers or peer-reviewed papers that I had gone through, and I had mentioned in previous slides. These are the papers I researched, and these are the papers that illustrate a lot of key concepts, and with case studies that will give you many interesting reads. I listed 10 main ones here that are most relevant. Please feel free to pause the video here to take a look at them if you are interested. So there's one reference slide here. Again, thank you very much for watching, and I hope to see you all in our next AI Made Easy series video. Oh, one more thing before I go. Please kindly put in any comments that you may have under this video if you see any comments, or if you see any mistakes that I made in these presentations. I've already noticed a few mistakes on this presentation and the part one, the last one, but I don't have the bandwidth to redo the whole thing. So I beg your pardon in some of those mistakes, and those mistakes, in my view, are not terribly impactful, so I'm letting them go. And I want to see if anyone discovered them and bothered to point them out to me. They're not crucial mistakes, but I'm always all ears to hear any comments or any corrections if you would like to let me know. Thank you again for your time and attention. Goodbye.